So here I've listed what I think are some of the big questions that people who work on subduction zones think about. So the first one is what controls the size of earthquakes? Why do we sometimes get a pretty moderate size event in the middle of a fully locked patch on the megathrust, while other times it will cascade all the way into a magnitude 9? What are the features that control the boundaries, especially along strike of that slip, and what do structural features on the downgoing plate contribute to controlling that earthquake size? And then the second one, in terms of great earthquakes in particular, can we expect to see sort of somewhat characteristic great earthquakes over multiple earthquake cycles for a particular patch on a megathrust, or is it really random? The third one, how dangerous is the shallow megathrust? So 10 years or so ago, a lot of us worked with this sort of misconception that the shallow megathrust was, it's like young, soft, wet sediments, it's got clays, it's probably creeping, not storing up a lot of stress. That viewpoint was confounded by the fact that land-based geodetic observations can't see the shallow megathrusts. So oftentimes that lack of resolution would mean that we marked it as creeping in a kinematic inversion for fault coupling. Now we're seeing that actually the shallow megathrust is really perhaps the most dangerous part of the megathrust. So I'll talk about why. And then what are the different manifestations of slow slip events, especially on different megathrusts around the world? We're seeing some areas have little small events every month, while other subduction zones like Sumatra, we can't find those, but we see these very large multi-decadal slow slip events. What's up with that? To get you oriented, here's where we are, with Singapore where I am marked. And what's happening here is we have the Indian-Australian plate subducting underneath of the Sunda block and underneath of Sumatra. And that slip is oblique. So it's partitioned with the thrust motion along the Sunda megathrust. And then the strike slip motion accommodated both on the Great Sumatran Fault that runs up the length of Sumatra, and also by a whole bunch of faults that are seeing diffuse deformation out in the Wharton Basin. And the Wharton Basin itself is likely seeing the formation of a new plate boundary, because the Indian and Australian plates, they don't want to stay together as one plate. They are breaking apart. And if you remember, there was a really large magnitude 8.6 strike slip earthquake out in the Wharton Basin that was probably part of that formation of a new plate boundary. In terms of data, our primary source of information is the Sumatran GPS array, which is, the stations are shown in this figure with the white dots. And we now have about 60 stations. At least I hope we do. We can't make it to Sumatra now to do maintenance, but we have about 60 stations that are continuously recording. Some of them were installed as far back as 2003, and quite a lot of them were installed in the last decade. And the really nice advantage of Sumatra is that we have this chain of outer arc islands, which means that we can install GPS stations right over the seismogenic zone of the megathrust, so we can get close to the action compared to some locations. And that means that since 2004, we've managed to record about 30 moderate to large earthquakes and probably a whole lot of smaller ones. And these are shown in this figure here. So the colored slip areas indicate the locations of the large events. You can see there's obviously a seismic gap here. And then the stars are the smaller ones that we've also managed to record. And if you are interested in modeling any of them, then Luja in her JGR paper has produced a catalog of all the co-seismic and post-seismic displacements from this huge number of earthquakes at Sumatra, which is, it's no mean feat, because the post-seismic signals in particular are all overlapping each other, so it takes a lot of wrestling to pull them apart. We also use INSAR, and then we also use paleogeodetic data that help us to extend the records back over multiple earthquake cycles. And most of the data that we're using are collected by Aaron Meltzner and his colleagues. If you're not familiar with coral data, the idea is basically that this particular species of coral like to grow to the low tide level on the islands. And so if there's a change in relative sea level, either from sea surface rise or from land height rise, then the coral will have to adapt to that. So if you raise relative sea level, then the coral has to grow extra fast to meet the new sea level. And if you subside the land, if you lift the land up, or if you drop relative sea level, then the top of the coral that's now exposed over the low tide level dies off. And so you can basically cut slabs out of these things, x-ray them at the hospital. They have growth rings like trees, and you can therefore use them as a kind of natural tide gauge. And you'll see, you can see from these bottom photos that land height change at these outer Arc Islands is very dynamic due to the tectonics. So in this figure on the left, you see these coconut palms, and they're now underwater because of long-term interseismic subsidence of that island. And then in 2004, during the Nias Simalu earthquake, that whole island popped back up again. And down here, you see those same coconut palms. So the coral are observing these ups and downs. So thinking back to those big questions, but now relating them more to Sumatra, the first main point that I want to make is something that we see pretty robustly at Sumatra, is that we have great earthquake ruptures on the megathrust that routinely are they stop along strike at what seem to be persistent barriers to rupture. So great earthquakes don't go over these barriers from one earthquake cycle to the next. And those persistent barriers to rupture coincide with structural features on the downgoing plate. The second main point that I want to make is just that the sort of concept of trying to observe steady state interseismic velocity seems to be quite difficult here, because even though we have these many decadal long time series, the coral observations show that from one decade to the next, those rates are not the same. And the best, most elegant reason for that we have is these very long-term slow slip events. And then finally, I'd like to persuade you that the shallow megathrust cannot be creeping. It's likely quite dangerous and very capable of producing tsunami earthquakes, along with a host of other slip behaviors. And oh, I forgot to mention one more thing at main point 1. The other thing that we see is that at these persistent barriers to rupture, we see very diverse slip behavior at those barriers. We see it after slip, slow slip events, moderate earthquakes, that they seem to produce a more diverse behavior than in the smoother patch between the barriers. I'm going to focus most of the talk on the Nias Simalu section, which is outlined here with the red rectangle, because this really nicely illustrates some of the points I want to make. Before I get into that, just going back to these structural features, this is a figure from Jensen and Jacobs' paper, and the different colors show different plate ages. And the history of the Wharton Basin is that long time ago, in the Eocene, it had a spreading center there that's now defunct, but it's left behind these long north-south trending fracture zones, across which we have these really distinct jumps in plate age, and therefore in plate thickness and in buoyancy. And that is being subducted at Sumatra. So where it comes to the points that these fracture zones are being subducted, you can have a really big jump in terms of the plate that's being subducted can go from thinner to thicker. You get these steps in plate age and thickness as you go along the megathrust, which I guess when I first started working on subduction zones, I had this kind of cartoon view in my head that you're subducting this nice smooth plate and we don't really have to think about what's on it, but actually we're subducting mountain ranges and topography and really big morphological features. Zooming in on the Nias Simulu section, I just wanted to point out the big structural features that we have here. So we have the 96° east and 97° east fracture zones, and the 96° east subducts underneath of the island of Simulu, and the 97° under the Banyak Islands. And then we have the investigator fracture zone, which is it's a broader, less well-defined region that subducts underneath of the Batus. This figure shows the slip patches for the 2004 Aceh Andaman earthquake, which of course extends way to the north of this figure, and then the 2005 Nias Simulu earthquake. And you can see from this, both this patch and this patch, so these two patches are both part of that rupture. It had a low slip patch in the middle, and based on our modeling, that low slip patch is quite robust. It's not just a resolution issue. The 2004 rupture ended at what we call the Simulu saddle. And this is a feature that's visible at the surface at Simulu, and that on the subducting slab is where the 96° east fracture zone is being subducted. The low slip patch corresponds to the subduction of the 97° east fracture zone. And the Simulu saddle, based on the coral data, has quite persistently terminated ruptures over multiple earthquake cycles. So you get 2004 like ruptures that stop with their southern termination there, and you get 2005 like ruptures that have their northern termination also at the Simulu saddle. And then at the southern end of the 2005 rupture, they also seem to stop somewhere around the general location of the investigator fracture zone. You can read a lot more about the evidence for the persistency of the Simulu saddle in Aaron Meltzner's papers. The 2005 Nias earthquake was not unique in its rupture. And what this figure shows is the coral uplift observations for both 2005 and then the great earthquake in the previous earthquake cycle in 1861. And what's really striking about these is that the coral displacements are really similar from one cycle to the next. And in fact, the previous cycle before, there's less data, but they also seem to suggest similarity in these ruptures. We can't tell whether there was also a low slip patch for 1861. We don't have enough data, but the general extent of these rupture areas and the magnitude of the earthquakes was very similar. So along with the co-seismic, the co-seismic didn't rupture to the trench. We know that for 2005, but there was very rapid afterslip. And this is a figure made by Chu Chang showing 9 years of cumulative afterslip after that event. And this afterslip was estimated in a joint inversion for viscoelastic deformation using his technique where he has these deforming blocks in the mantle wedge to approximate viscoelastic deformation. Most of the afterslip was located right up dip of the co-seismic, and there's this very pronounced line of aftershocks right between at the boundary between the afterslip and the co-seismic. There may also be some afterslip down dip, but there's trade-offs between that and the viscoelastic. So I'm not sure that it might be there. It's not completely robust. Moving back to the Similou saddle, that barrier between ruptures from like 2004 and ruptures like 2005, we see a kind of pattern of having moderate earthquakes at that patch. And here's some examples from Paul Morgan, where he's got what we call sibling earthquakes, because they're very similar. There's one in 2002 and one in 2008, and they're these two overlapping earthquakes right at that boundary. And they correspond to a morphological high in the subducting plate. That's also where the 96-degree east fracture zone is. That feature is pretty robust from seismic reflection and tomography data. And there's also those earthquakes are where there's a little asperity that seems to be surrounded by somewhat creeping medium on the megathrust. And the 2008 distribution was based on GPS and also this really cute interferogram. Moving to the low slip patch in the middle of that. Oh, yeah, there we go. In the middle of that big rupture patch, we also see a tendency for moderate. I shouldn't say a tendency. There's at least one that we can actually model, and potential for more in the seismic catalog. And this one, which is based on GPS data, fits the 2010 earthquake, fits right into the middle of those two low slip patches. We also can start filling in this patchwork of slip with a very, very long slow slip event. So what you're looking at here in this figure is, on the left-hand side, these are coral observations for the period 1981 to 2005. So the few decades before the 2005 earthquake. And these guys are doing what we expect them to do interseismically. They're subsiding at rates that we would expect. What you see on the other side is and we also, the period of before 1966 is also very similar to what we see on the left-hand side. It's just that there are fewer data. What you see on the right-hand side are the coral rates for the period 1966 to 1981. And you can see that suddenly in this area of the Banyaks, they started going up. And that's not interseismic behavior. And the only way that we can really come up with to model that, and we thought of a lot of different things like big sea surface features like Indian Ocean dipole and so on. But the most simple way that works well is to put a big, long, slow slip event where in this orange patch. This, by the way, is work from Louisa Sang, who's in the UK now. If you put a slow slip event there that's lasting for 15 years, you can model the coral data. And that fits right down dip of the 2010 event, so filling in our patchwork quilt. We know empirically that there's a relationship between the magnitude of a slow slip event and the duration of that slow slip event. And quite nicely, this Sumatra event shown up in the red at the top does agree pretty well with those empirical relations. We also have some evidence for an even longer slow slip event in the shallow part of that section. And this is based on, so what you see in the time series are coral data, which for several decades, these correspond to the locations shown in the map. And they're just trundling along at one rate. And then in 1829, suddenly the rate changes, and then they have a new subsidence rate. And initially we thought, maybe we can model this by changing the down dip extent of coupling on the megathrust. So if we change the width of the locked zone, then maybe we can change the rate of subsidence. And you can, Louisa published some exploration of that idea. The problem with that is you have to have quite unphysical changes from fully locked to fully creeping at the down dip part. And so Rishav Malik instead came up with probably a more elegant solution that you can also fit these data by having a large slow slip event in the shallow part. That part has hosted Afterslip, so it looks like it's velocity strengthening. So he gets into invoking movement of fluid to destabilize that region enough to have a slow slip event. You can find out more in his paper that's currently submitted. We haven't found any evidence at Sumatra, however, for smaller, more regular Cascadia or Japan-like slow slip events. What you see in this figure is the sugar time series for the whole of Sumatra, having removed all the known tectonic signals. This is work that Luja did, and we hoped that we would look at the residuals and we would see something interesting in terms of slow slip events, but they're like really boring and really flat. And maybe they are in there, we just can't see them, and maybe they exist, but they're just too small for the network density that we have. 60 stations is not that many for a big area like Sumatra. This figure shows the minimum magnitude that we would be able to pick up, and it's something like a 6 or even larger. Also in the shallow megathrust, we've seen that Sumatra has had a history of producing these shallow tsunami earthquakes. So a tsunami earthquake is an earthquake that produces a much larger tsunami than would be expected based on its seismic magnitude. And the two figures at the top are for the 1907 Nyasimalu tsunami earthquake. And this was an earthquake and a tsunami that it devastated Simalu at the time. And it's the reason that in the 2004 tsunami, most people on Simalu survived, because it created folklore that was passed down and meant that everybody spontaneously evacuated from the coast when they felt the 2004 earthquake. And what Stacey did for this was scour old newspapers, old records from the Dutch, and try and find eyewitness accounts of this event. They then did tsunami modeling to try and recreate some tsunami that would agree with the eyewitness accounts. There's also, of course, pretty coarse, but it's kind of interesting that the high slip patch is again right at that point that the 96° east fracture zone is being subducted under Sumatra. What that earthquake may look like, to know, we can have a quick look at the, sorry, I've lost my cursor somewhere. Okay, at the 2010 Mentawai earthquake, which that killed, unfortunately, 500 people. It generated a tsunami that had a 16-meter run up on the islands, and that earthquake was surprising at the time because it was so shallow. It ruptured up to about 6 kilometers deep in this area that we thought was all wet, young sediments. And yet it managed to generate enough slip because of that low rigidity to generate this very large tsunami. So it's clear that the shallow part can rupture co-seismically. They're slow ruptures, but they're still seismic, and they still produce big tsunamis. So what is the coupling at that shallow part of the megathrust? Well, we without knowing anything about the frictional properties of that, we can still say that it's unlikely to be creeping. And this is a paper from Eric Whimsey which it's really common sense, but for some reason, many people who were doing inversions for geodetic inversions for interseismic coupling forgot about it for a while, or it was just too complicated to think about it. But if you fully lock the down dip part of a megathrust, then you can't possibly creep the top part, because the part below it is stuck. So the top part can't move. It's in a stress shadow. And so what Eric's done is formulate a new way to do these inversions that incorporates these physical stress-based constraints into the geodetic inversion. And it pretty much means that if the down dip part, like we see at Sumatra, is locked, then we have to assume that the shallow part is not slipping, even if it frictionally could creep. It doesn't have the stress drivers to creep. I have no doubt oversimplified things far too much by describing this story of like, oh, we have these subducting features that work as persistent barriers to rupture, and on them we see very diverse slip behavior. Between them we see these great earthquake ruptures. I'm saying that based only on a few earthquake cycles going back, so which is a snapshot in time for tectonics. But there are things that are worth thinking about and modeling some more. The fact that this may be too simplistic is also illustrated by the Mentawai area to the south, and that had great ruptures in 1797 and 1833, we know from the coral and historical reports. But in this earthquake cycle, the Mentawai patch seems to be breaking up into in a kind of slow patchwork. It's not having that great rupture that was forecast. And so we had the 2007 Bengkulu earthquake. In 2008, there was this little 7.2 that like ruptured right in the middle of this lock patch that we know is loaded and ready to go, but it still didn't cascade into the really big earthquake. It's an illustration of needing more marine geophysics data probably to understand if there's some morphological feature there that bounded the slip, or what was the reason for that? Is there any reason, or is it just random? And then there's the 2010 shallow earthquake rupture. So I'm definitely not advocating for really understanding this, and there's a lot of things we don't understand and randomness, but it's useful to look at some of these patterns. And I think it will be useful to think about this in the context of other subduction zones and look for other evidence of whether this is some of these things unique for Sumatra, or do we see them in other places as well. I'm right at my 30 minutes, so I will wrap up. I will put it on the Slack, but I did want to advertise that we have some open positions in Singapore. We have quite a few PhD positions. They're fully funded with stipends in tectonics and in thinking about the solid earth effects on sea level rise. There's a big cluster higher in sea level that person would be a member of. And we also have a couple of postdoc positions. One is for fresh PhD and one is for someone with about 5 years of experience, and they are quite open in tectonics, hazards, disaster response, but using geodesy. Thank you.
Okay, thanks, Emma. That's great. I mean, I don't know, I'm going to clap. But,
thank you.
But we could, otherwise we can do the little button reaction thing, right? You can clap there. But so I guess there's an opportunity now for questions and discussion. So there's so if you have questions, type them in to the chat, and I will try and relay those on to Emma. So first we've got one from Ed Rhodes. Ed asks, how certain is it that persistent barriers are truly persistent? how many events are available to assess this?
The coral data, you can have a very long conversation with Aaron about this, but the coral data do go back over multiple earthquake cycles. The problem is the further back in time you go, the less good the data are, just because of erosion, and you just can't track them anymore. So at the moment, I sort of 3 earthquake cycles in a fairly robust way, and maybe more, but in a more fuzzy way. And that's often when there's very few data points, it's really based on kind of, you can't do a really good slip inversion. It's based on looking at where you think the endpoints might be, based on only vertical data.
Great, thanks, Emma. I got a better feel during your talk, actually, later, from after I typed the question. So that was
okay.
Great. So we have a question from Yingfeng Zhang. So thanks, Emma. During the process of the coral data, processing of the coral data, how do you remove the effects of sea level change with time, and what is the precision of these data?
Okay, I should be really clear that my group model the data and we do not collect it. I have never cut a piece of coral in my life. So Aaron is really the expert in this. For the question about the sea level change, that's a tough one. For kind of last century data, they simply remove a linear rate of 1.8 millimeters per year. There are some known ocean effects too, such as big Indian Ocean dipole signals that they know about and just sort of dismiss from the record. Usually, it's just based on ocean effects don't do this kind of thing. Like if you have a rate that's like this and then a rate that suddenly changes, it's difficult to think of an oceanographic effect that would be like that. But the whole rate could be a little off due to sea level rise. For Louisa's paper, where we were looking at modeling these interseismic rate changes, what she did was take the altimetry data for as far back as possible, just to estimate what the potential noise, what the potential level of uncertainty is in the coral data based on present day ocean signals, and then create error bounds for the coral data based on those. But for further back in the past, we don't have a good way of doing it. The precision of the coral data depends quite a lot on the individual coral. Some corals are really pristine and the coral scientists get really excited about them because they're so beautiful. And then other corals are quite eroded and messy and a lot less precise. It's really difficult thinking about uncertainties for coral data.
Great, thank you. So Laura Gregory asks, in relation to the moderate earthquakes on asperities, so for example in 2002 and 2008, what is it that makes the high on the subducting plate and asperity? Do you think it has different physical properties?
Yeah, that's a really good question, and certainly you can terminate these ruptures due simply to geometry, and we saw that really nicely for the Gorkha earthquake in Nepal as the case example of bounding an earthquake rupture due to ramps and flats on the fault. And in terms of frictional properties, I don't know. I think we have a lot more to think about in terms of what's velocity strengthening, what's velocity weakening, especially in the shallow part of the megathrust. The reason that I say it's an asperity in terms of coupling is because we've modeled the long-term coral data, and they show quite nicely that there does seem to be a little asperity there that's got some creep around it. in some ways, I feel like we've picked all the low-hanging fruit for geodesy for Sumatra, and what we really need now are really good marine geophysics data, like OBS, to really carefully map the seafloor and try and figure out what smaller features look like.
Great.
That's not a great answer, I'm sorry.
Yeah, no, I think it's an honest answer, isn't it? So that you don't, so Max,
I'll leave the earthquake physics people to figure that one out.
But yeah, I guess in some parts of the world they've drilled holes as well to try and access it, but it's obviously hard to get to the right depth. So Max Werner, it's a comment, not a question. I'm not sure I should even read it out, but I'm going to. I think Thornley argued convincingly that earthquakes can span subducted ridges, at least in some locations. See the 2007 Solomon Islands earthquake.
Yeah, I'm not ruling out it not happening at Sumatra. Earthquakes always seem to do worse than our imaginations. So.
He also says, wonderful talk and thank you. So in a later comment, still not a question. So John Elliott says, thanks for your talk. In terms of the dip coupling that you currently have in revision with Eric, is it possible to promote creep induced from along strike stresses, the forces of the overriding plate, the stress from deeper creeping portions below the locked area, or overshoot from previous earthquakes? There's quite a lot of potential mechanisms there.
I assume so.
Presumably
Eric
whatever,
Eric does not get into that in his paper, but I assume all of those could be possible, yes.
Right, thank you. We'll take a few more questions. They're coming fast now. So Tim Craig says, thanks for the talk. Could you say something more about the longer term dynamics behind the emergence of the islands, Simeulue, Batu Nias, and how you think this may relate to the interplay you discussed between the subducted topography and the megathrust behavior?
I wish I could answer this question. I don't know. This is really frustrating, actually, because there's no evidence that anyone can find for permanent uplift of the islands over multiple earthquake cycles at Sumatra. And they've looked for it. There's a place on the very southern mainland of Sumatra where there's really beautiful terraces, but there's nothing on the islands that suggests this is why they can look at these earthquake cycles using the coral, because there's no permanent uplift of those islands. That there must be a reason for them being there. And also you may have noticed that the Batu Islands, which are at the location of kind of a bend in the megathrust and a subducting feature, are further away from the megathrust. There must be a reason for that. There must also be a reason for why on Sibling, which is one of the islands from the south, they don't have much coral data there, because it's, instead of like beautiful flats where they can look for coral data, it's more steep cliffs. There must be a reason for that, but I don't know. I don't know. I don't think anybody has yet figured out why.
Great.
It's a good
Thank
question.
you. Good, interesting question. I had a question that I skipped over earlier, which was about the kind of how you transfer the knowledge from this system to other systems. And I guess I'm thinking about the Himalayan megathrust, which may, the coupling patterns that Vicky Stevens and Philippe Avouac came up with look on the face of it very, very different potentially. Do you think that it's very hard to transfer that knowledge, or do you think things can be transferred across?
I think there is some room to transfer. So Aaron and Belle Philibosian actually have a paper in review now that focuses on trying to it's a review paper on kind of do we see this kind of persistency and relationship with structure on other subduction zones around the world. he sent me the paper. It's super long, so I didn't get a chance to read it before my talk, but I believe that they do their best to pull out all the data in the literature to show that there are other examples around the world of some of the things that we're seeing at Sumatra. And Sumatra has been such a beautiful test bed because we had so many earthquakes to look at the kind of how the patchwork fits with the very recent earthquakes when we have geodetic data. But I think the general theme, they do see ways to extend that to other areas. The paper's in press, so Filibosian and Meltzner coming out soon. Might tell you more.
Look forward to seeing it. So I think we will wrap it up there. Thank you so much, Emma, for joining us, and enjoy your end of lockdown party. It's 1 minute to midnight.
Some of my neighbours are having 11:59 p.m. cocktails. I don't think I'm going to stay awake for it. But